Okay, I think we're probably good to get started at this point. So it's a pleasure to welcome today Chris Garling to give our lunch talk. So Chris is a grad student at The Ohio State University working with Anna Capita, and his work focuses on using dwarf galaxies to put constraints on cosmology. And that's what he's going to tell us about today. And we can't see Chris because he doesn't have a camera on his computer right now, but we can see his slides and hear him. So take it away, Chris.
All right, thank you for the nice introduction. The title of my talk is Constraining Nonlinear Cosmology with Extragalactic Satellites, but I have some bonus content on environmental quenching, which I may or may not get to today. So I'm going to start off with some background, both observational and theoretical. And then I'm going to talk about the observational work that I did during my PhD as a part of the LBT-SONG survey. Then I'm going to transition into talking about theoretical work that is oriented to interpreting the observational results. I'll then discuss some future plans, things that I'm excited about for current generation surveys and next generations. So observations across a large range of astrophysical scales, from things like globular cluster dynamics to galaxy lensing, require a dark matter component. Unfortunately, there are no excellent candidates for a dark matter particle in the standard model. And so explaining dark matter, perhaps with the exception of something like sterile neutrinos, requires an extension to the standard model. And so there's this link between understanding dark matter and understanding fundamental physics. On large spatial scales, generally above a few megaparsecs, structure is well constrained by, as I said before, clustering and lensing. And these observables are well fit by the cold dark matter model in combination with a cosmological constant for dark energy. Because of these strong observational constraints, all realistic dark matter particles must behave similar to lambda CDM on large spatial scales. However, there's still a lot of room for changes on smaller nonlinear scales. This is because there are fewer observational probes, and they're also generally fraught with higher degrees of systematics that makes interpreting them more difficult. And so some of the observations that can constrain cosmology on small scales include substructure lensing. This is looking for basically flux anomalies, for example, in strong gravitational lensing around clusters. And they can probe directly dark matter halos. They don't have to have galaxies in them. And they can be sensitive to quite low masses, but it generally requires a pretty specific lensing geometry, which means that there aren't huge samples for this at the present moment. There's also Lyman alpha forest, which is more of a high redshift probe. This looks at line of sight absorption due to neutral hydrogen along the line of sight. And so this allows you to probe basically small clusters of matter. And it can be also quite sensitive to low mass baryonic structures. Then in terms of inter-halo constraints, we can look at things like globular cluster dynamics. So if the density profile of the dark matter halo is one way or another way, it implies something different for how the dynamics of basically mass tracers like globular clusters should behave. But today we're going to be focusing on dwarf satellite galaxies, specifically talking about abundances and luminosity functions. And so in an ideal world, we would get predictions for all of these quantities as a function of the microphysics of the dark matter. But in general, because these cover a wide range of observables and also redshifts, it can be difficult to get all of these in one go. Generally, they require different theoretical approaches. So on the dwarf galaxy front, these are interesting for dark matter constraints because they are the least luminous galaxies and they live in low mass dark matter halos. So the plot shows the relationship between the halo mass on the x-axis and the stellar mass on the y-axis. And I've kind of marked the point where most galaxy surveys can't probe any lower masses than this. We'll come back to this a little bit because our methods depend somewhat on what happens on these lower mass scales. But the idea is that because these are low mass halos, they correspond to small spatial scales in the early universe. And so these are more or less direct probes of what nonlinear cosmology is doing. This is entirely possible in the Milky Way with recent surveys, including Pan-STARRS and DES. The plot is from very nice work done by Carnegie postdoc Ethan Nadler, which shows on the x-axis the absolute magnitude, which is just the luminosity of the satellites. And then on the y-axis is the cumulative number of satellites brighter than the x-axis value. So lower on the right-hand side is brighter. However, this method allows us to place constraints on some dark matter models, but there's a lot to be gained if we can get outside the Milky Way. A difficulty in recent history has been the presence of the Large Magellanic Cloud. Simulations show that Milky Ways don't often have Large Magellanic Clouds, and results from DES, for example, have shown that a number of the satellites now associated with the Milky Way were actually satellites of the LMC before it fell onto the Milky Way. And so this, in concert with just general concerns dealing with cosmological variance, leads us to want to apply similar methods outside of the Milky Way. However, these studies are subject to different observational challenges than several of the Milky Way studies are. They require large aperture telescopes so that you can go to these very faint magnitudes. And they also require large field of view imaging cameras. This is because dwarf galaxies can be spread across the entire virial volume and beyond, in the case of things like backsplash galaxies, which we won't talk about today. But in summary, there are relatively few camera and telescope systems which are well suited to do this kind of work. And we'll see a couple of them today. There are a couple surveys in progress, which are somewhat aimed to be like LSST precursors. But the caveat there is that they sample much smaller volumes than LSST will. And so these are great opportunities to develop methods that will then be applicable at LSST scale. And the full volume of LSST will give us a great number of host galaxies around which we can search for these orbiting satellite dwarf galaxies. And so on the right, I'm showing predictions from Burçin Mutlupakdil's talk. I work with her in MADCASH. What she's showing here are predictions for the completeness function of an LSST-like survey at a distance of 3.5 megaparsecs. So the color, as indicated by the color bar on top, indicates how the likelihood of detecting a dwarf with a given size on the x-axis and luminosity on the y-axis. And one thing that's interesting that you don't see in Milky Way studies is that there's a drop-off at small sizes. This is due to photometric blending. Because these galaxies are much further away, the stars get blended together and you can't separate them, and it reduces the overall signal. And so we'll talk about this a little more later in the talk. And so I'll begin by discussing my observational work on the LBT-SONG survey. So this is an example of data from our survey. This is for NGC 4214, which is roughly an LMC mass galaxy at 3 megaparsecs. And what I like about this figure is that it shows, you can see basically this sea of red giant branch stars around the center of the galaxy. And this shows the sort of point source depths that we're able to achieve. Generally, we get 50% complete at 27.5 magnitude, which is comparable to what 10-year LSST depth should be. And so this survey actually used completely recycled data, so no new data were taken for this survey. A major limitation is that we only have a single pointing, and there are only 30 arc minutes on a side, which corresponds to a spatial scale, depending on the distance of the host, between 20 kiloparsecs and 40 kiloparsecs on a side. So we're really only getting the central portion of the galaxy here. But predictions from simulations show that the radial distribution of satellites should be fairly centrally concentrated. So by looking at the middle, you stand to hopefully capture a decent portion of the satellites. And we'll look exactly what this limited volume does to our predictions later. And so in total in the survey, there are about 20 hosts. I did the data reduction for the full survey, but I also analyzed the nearest 6 hosts that are within 5 megaparsecs, because these hosts are close enough that you can use point source methods to detect the dwarfs. The more distant hosts are being worked on by Bianca Davis, another one of Annika's graduate students, and she had kind of a preview paper on NUC 628, which is out. And so I'm not really going to talk about the methods that we use to detect the dwarfs, just because they're fairly standard and not all that interesting. So instead, I'm going to focus on what new things I developed for this survey. And so from the beginning, this survey was closely tied to theoretical ideas that Annika and I had. And so one of the main challenges to comparing these types of surveys against theory is that they're highly incomplete. So as I showed in that previous figure from Burchine, your completeness is a strong function of both the size of the galaxy and its luminosity. And so the standard way that you attempt to measure this is by doing image simulations. So here what I'm showing is at left, a real dwarf galaxy in our sample, and at right is an image simulation. So how this works is you specify a star formation history. It can be complex if you want. And then you sample stars from isochrones star by star until you build up the luminosity that you need. And then you inject these into the science images with the real measured PSF in order to create these mock galaxies. Then you run these mock galaxies through your photometry and your detection pipelines, and you Monte Carlo this many, many times, and you see how often galaxies with particular properties are detected. And so here I show 2 other examples. Sorry, this is like a V-band absolute magnitude of -12, so it's roughly 4x luminosity. And this shows 2 -8s. The left one has a surface brightness of 25 magnitudes per square arc second. So it's in the world that I live in, this is somewhat high surface brightness. And at right is also a -8 magnitude, but this one has a surface brightness of, I believe it's 29 magnitudes per square arc second. So it's much lower surface brightness. And so when you sample many of these galaxies and you recover them or don't, you can build up statistics like this plot shown on the left, which is just exactly the same space as I showed before from Burchine's paper. And you can quantify how likely you are to detect dwarfs of different properties given the depth and quality of your survey. And so in terms of overall depth, we're actually reaching kind of similar limits as to what Burchine expects from, this is 10-year LSST data. But you'll notice that here, this is kind of what I refer to as the danger zone, because at low luminosities and small sizes, things become highly blended. And so it's very difficult to recover them with point source methods. And so you can see that we are actually not doing as well in this regime as LSST is predicted to. And this is a function of the seeing of our images. We have image PSFs that are like 1 to 0.9 arc seconds, full width half max. And LSST is predicted to do much better than that. So maybe 0.4 or 0.5 arc seconds. So the stars appear much angularly smaller, which means that blending becomes less of a problem. This image simulation method is quite robust, but it's slow because you have to do point source photometry, which is basically the slowest part in the analysis pipeline. And so can we produce similar results, but do it much faster? This is not really a huge issue for LBT-SONG, but it is an issue for things like MADCASH and looking in the future, LSST, because these are going to be much larger volume surveys. And so at this time, efficiency becomes relevant. As part of this work, I developed an emulator that operates at the level of photometric catalogs. So photometric catalogs are just tables with star positions and magnitudes that come out of your photometric pipeline. And so it uses the results of these photometric pipelines and then just injects basically artificial stars into the catalog according to prescriptions that I'll talk about soon. So at left shows just the stellar positions of a simulation of a magnitude -9 dwarf before you apply photometric completeness effects. So this is done with artificial star tests. At right is what it looks like after you account for the photometric incompleteness. And so you can see, I think there are like something like 10 to the 6, so like 1 million stars in the left panel, and only maybe 100 or something make it through the completeness effects. However, when we run this through our detection pipeline, it's still much too significant. So if we do a similar image simulation with the exact same catalog, this significance over here in the color bar shows basically the amount of significance over the standard deviation of the field. This is not our final statistic, but it's the clearest one to look at. And so this shows a peak significance of maybe 20 sigma, when in the image simulations, we find that it should be closer to 6 to 8. So that's a large discrepancy. And so there's another photometric effect that we haven't taken into account, which is that in regions of higher surface brightness, you are less likely to detect stars. So in the center of the dwarf, where there are potentially a whole bunch of stars blending together, it is much harder to detect a star of a given magnitude than it would be if that star was out in the middle of the field, right? And so what we do is we add in what is essentially a model that reduces the photometric completeness value dependent on both what the magnitude of the star is and on what the local surface brightness is. And so after we apply this additional reduction of the photometric completeness, we get results that look much more like the image simulations. And so you can see now we're sort of in the regime of 6 to 8 sigma. And this level of variance is also shows good agreement between the results of the image simulations. So depending on the location in the images and also on the stochastic sampling of the RGB, because stars on the RGB have a relatively narrow range of initial mass. And so you're going to sample far more things on the main sequence than you will on the RGB. And so for faint satellites, generally below -7, it really matters. It matters slightly less, maybe at -9, but you'll end up with more or less stars on your red giant branch, depending on just stochasticity. And so now we can look at how the catalog simulation compares to the image simulation. So at left is the completeness function for the image simulations, and on the right is the same thing, but for the catalog simulations. And so if you look at the bulk trends, the catalog simulations actually capture it quite well. This regime out here is fairly easy to do because you're just limited by basically overall surface brightness. There's nothing particularly difficult about modeling the regime of large size and high luminosity. Where all of our blending models matter is for small sizes and low luminosities. And so you can see that we reproduce quite well this drop in completeness as you move to smaller sizes. And this is very important because the most cosmologically interesting dwarfs are things in this ultra faint regime, things kind of -8, -7, and fainter. And so later we will use the results of this calculation to correct our theoretical predictions. So it's important that we understand this completeness function. I'll comment very briefly on the difference in the scatter between them. Part of this is just due to Monte Carlo sampling. So there's like there are like 2,000 galaxies in total in the left panel, and there are like 6,000 in total on the right panel. But what's more significant is that in the image simulations, we're placing galaxies directly into the science images. But for the catalog simulations, we are putting it into the catalog, right? So diffuse light that isn't due to stars doesn't show up in the catalog. Bright galaxies that could blend with other things, background galaxies, they don't show up the same way in the catalogs as they do in the image simulations. And so there's some loss of realism here, but it's mainly to do with the scatter. We reproduce the main relationships quite well, which is mostly what we want. It would be nice to try and deal with, for example, this is maybe 80% completeness, whereas we're reporting 100% completeness here. It would be nice to look into modulating this slightly more correctly, but we didn't do this for LBT. Oh, and I didn't say, but the catalog emulator is roughly 100 times faster than the image simulations, and that's for like a very experimental implementation. So it could probably be even faster. In the end, we didn't end up discovering any new dwarfs in this survey, which made us kind of sad. But the real question is, should we have expected to find new galaxies? A null detection can be interesting depending on what theory expects. And so now I'm going to transition into talking about my theoretical work. And so once again, we're going to look at Ethan's plot here. The main observable that we want to model is this cumulative satellite luminosity function, this total number of satellites brighter than a given luminosity. And this is just the cumulative integral of the differential satellite luminosity function, which I'll write as dn dmv. At minimum, what we would like to have is an expectation value for our survey and a credible interval of whatever significance you prefer. Often what is done for this is you would try to draw similar systems from a Monte Carlo population that is formed by forward modeling. So this is something like picking similar systems out of simulations, running zoom-in simulations, or looking at semi-analytic model output. Cosmological simulations are limited in this regime because they generally only reach ultra-faint magnitudes for small volume zoom-in simulations. And so some nice work on this front has been done by Alison Brooks and her group. And I've been thinking about it, and we ended up not going the semi-analytic model route because in general, they do more than we require for this type of analysis. Semi-analytic models contain a lot of, they make a lot of additional predictions. So they look at things like stellar and gas phase metallicities, central black holes, and basically things that we don't have observables for, right? And so, and there's the additional complication that we know to some degree the observational properties of the system. So the most important of those are the properties of the host. We probably have a stellar mass or a luminosity for the host. And so what we would really like to have is a prediction that is specific for every host, rather than looking at, we have this huge population of things with various properties, and now let's select out a subset, which hopefully will look like the thing that we actually have. And so this is the approach that we took for LBT-SONG, is a very system-specific modeling approach. We do this by what I'm going to refer to as a semi-empirical model, in contrast to the semi-analytic models. And so the way that this works is that we relate observational quantities, which are either what we have or what we want, to theoretical quantities, which are necessary in order to do the calculation, but which we don't have good constraints on. And so the way that we do this is that we formulate a joint probability distribution that's based on scaling relations. So another thing to mention at this point is that we're only really interested in low redshift quantities. You can't, because the cosmological information comes from very low mass galaxies, you can't detect them at high redshift. And so we don't need something that has robust and strong redshift dependence. And the scaling relations in general are only available at such low masses at low redshift. And so it kind of matches up pretty well. And so the way that we calculate this is that we have this joint distribution. What this is a joint probability distribution for the luminosity. The upsilon here are basically hidden theoretical quantities, and the theta are observational quantities which we typically have, but these are formulated as probability distributions also. So what you might have for the host is a stellar mass median and an uncertainty range. And so what we do is we set this up as this joint probability distribution, and then there's the term for the subhalo mass function. This is what actually gives us the abundance of satellites, because this is normalized to results from simulations or predictions from, for example, extended pressure sector theory. And so we set it up with these types of parameters. This is fairly simplified, and so I hope I haven't made any dumb errors in the notation. But calculating the differential satellite luminosity function then just amounts to a marginalization over the uncertainties in these parameters. So examples of the theoretical quantities include things like the halo mass of the host and the halo masses of the satellites. And observational properties include the stellar mass of the host, the stellar masses of the satellites, and sort of higher order galaxy evolution terms. So, for example, the stellar mass to light ratio and the color distribution. This is how we map from stellar mass to luminosity space. And so after we marginalize this joint distribution over these nuisance parameters, it just gives us the differential satellite luminosity function. And this is only requires a multidimensional integration. And so it's fairly simple with, for example, Monte Carlo integration techniques. And so now I can show you some observational results from the survey, as well as what our theoretical predictions are. So in blue is what I predict for the overall cumulative satellite luminosity function of the survey. So this is the sum over all 6 hosts in the sample. And this is without any observational corrections. Then we include a term in the joint probability distribution which relates halo properties to the galaxy size. We need some galaxy size distribution in order to make use of our completeness function that we looked at earlier. And so when we include this completeness term, you can see that it curtails our cumulative satellite distribution starting at around -8. And then we really don't have anything much fainter than, or we shouldn't expect to have anything much fainter than about -7. Then we additionally add the effect due to our restricted field of view. So like I said before, we only have roughly the central 20 to 40 square kiloparsecs. We don't have full virial volumes. And so we have to assume some radial distribution for what the distribution of satellites is as a function of radius. So that we can then say, this is our cutout field of view. How many satellites should we expect to see in that field of view? And so that gives us our final green line here. And then additionally, I believe these are 1 sigma ranges here. In black then is our observational result. We didn't discover any new dwarfs, but there were 2 previously known within the volume of the survey. And you'll notice that the overall number agrees quite well with our prediction, but both of these observational dwarfs are relatively bright. One's like -13 and one's about -12. And so these are basically classical dwarfs. And our model predicts that we should at most have maybe 1. I think having 2 is like an 87% interval or something like that. But because the statistics are so low, this actually, I don't take a whole lot of stock in this personally. I think it's going to be much more interesting when we apply this to things like MADCASH, Saga, and LSST, which will have much more significant satellite samples. A side effect of the way that we formulated the problem is that different quantities are related to each other indirectly. So for example, the galaxy size is related, specifically it's related to the virial radius, which depends on the halo mass, right? And so what I'm showing here now is the 2D slice of probability. This is for a Milky Way like system, and so the 2D histogram is just my prediction for the probability distribution in this space. Shown in black are local volume dwarfs. It would have been nice to do only Milky Way ones because there are like some extra bright things up here that aren't Milky Way. But in orange are predictions from the DC Justice League simulations, which are some of the only ones that go to these types of faint magnitudes. And so overall, like this isn't a robust analysis. I just made this for fun. But overall, we actually see pretty good agreement between the distribution of points in this plane. It also, I hesitate calling it a prediction because it's more just, it's something that comes out of the model due to the choices that we made. But we predict a fairly significant portion of dwarfs that are fainter, or sorry, lower surface brightness than 31 mags per square arc second. That's what this line here is. And this overall quantity is actually quite comparable to what Ethan calculated in his model. I believe the number was something like 30% of the dwarfs should be lower surface brightness than 31 mags per square arc second. And that's actually quite close to the overall proportion that we see as well. And so there's potentially a lot more that we can try to do with this probabilistic framework. It has a lot of components that can be very easily changed. So these are pretty much all just, most of the things take analytic forms. Some of them you have to calculate numerically and interpolate, but the number of those is relatively low. And so generally what this gives us is a large amount of flexibility in terms of what we make our models. So one thing you can imagine doing is varying the halo mass functions or the sub-halo mass functions for different predictions from dark matter models. Well, what I'm showing in this figure down here are divergences from lambda CDM and warm dark matter. This is calculated with Andrew Benson's 2013 extended Press-Schechter style formalism. And so in terms of the power spectrum, you can see that warm dark matter creates a large divergence at small scales. And this corresponds to a sharp or fairly sharp cutoff in the halo mass function. I think for this model, this is a 1.5 kilo electron volt thermal relic. So I think this cutoff is something like 2 × 10⁸. And then when I use this halo mass function and the sub-halo mass function that comes out of it, you can see the difference in the predicted satellite luminosity function on the right. And so I haven't changed any of the baryonic components. As it happens, most of them are not very well constrained in this region. And I'll talk about this a little bit more if I have time at the end. But you can see that in this ultra faint regime that I've been trying to highlight, kind of -8, -7, and fainter, it naturally produces this truncation. And so one of the things that I'm excited about is implementing more of these alternate dark matter models. Some of the ones I'm interested in at the moment are self-interacting dark matter and fuzzy dark matter, or scalar field is another name for it. But the highlight is that it's fairly easy to do this. If you can get predictions for the halo mass function and you can figure out a way to propagate it into the sub-halo mass function, then it's not really all that hard. Oh, and I'm also interested in trying to do inference with this. So far, that hasn't been a focus because the observational samples are fairly small. In order to do inference, you would like to have a statistically significant sample. And so this, I think, will be interesting once we have a population of, I want to say 10 to 20 relatively well understood dwarf galaxies with well-measured completeness functions. Some of the work that's being done by other groups on this don't have great completeness functions, which makes it quite hard to put the theoretical observations, the theoretical predictions into the observation space, right? So that step is fairly important. So to summarize, we discussed at the beginning why dwarf satellite galaxies are interesting in terms of trying to learn about cosmology on nonlinear scales, mainly because they live in low mass dark matter halos, and they also trace the growth of substructure. Excellent work has been done on the satellite galaxies of the Milky Way, but it's very interesting to try to extend this outside of the Milky Way to try to escape some cosmological variance, but also to probe a different range of host masses. So I won't discuss this in very much detail, but at these low dwarf masses, there's some degeneracy between the baryonic component of the model. So, for example, what stellar mass do you expect a 10⁸ halo to have? There's some degeneracy between that baryonic component and the subhalo mass function. And so one way that you can try to get around this is by looking at hosts that themselves have different masses, because we expect that the baryonic component will be semi-constant across all of the hosts that we look at, but the normalization of the subhalo mass function is dependent on the halo mass of the host. So you can attempt to disentangle these two components by sampling a wider range of host masses. this is one of the reasons that both LBT-SONG and MADCASH are focused on these lower mass, kind of LMC mass hosts. We discussed how it's really important to understand the completeness of the survey, because this is what allows you to robustly compare your theoretical predictions against the observational results. And one of the reasons that I think this approach is interesting is that it's quite fast. And so potentially what you can get out of this is a prediction that is specific to every single galaxy in your sample, for very large sample sizes. And I think this is an approach and interesting way to try and do this. There are some additional model components that I'm kind of interested in. I do some work on environmental quenching, which I don't really want, I have slides for it, but I don't really want to go into it because I want to leave time for questions. But you could imagine including environmental effects in this type of model. So one of the things that I assume is a color distribution for the satellites, which then maps into a stellar mass to light ratio. And so you can imagine having a color distribution which depends on the halo mass of the satellite, right? And so you could factor in a consistent way things like reionization quenching, or I think it would be quite a bit harder to try and model like ram pressure stripping or other, higher order things like this. But you could probably at minimum try and do reionization quenching in this way. And so I think that's all I want to talk about. 15 minutes for questions sounds about good. Do you agree, Andrew?
That sounds good to me, yeah.
Okay.
Great, thank you, Chris. Yeah, so we have plenty of time for questions if people have any. Ethan, you have a question?
Yeah, thanks, Chris. That was a really good talk. I have two related questions. I guess going back to your slide with the comparison, where you had the completeness corrected comparison to the observations. Yeah, this one of the luminosity function. Yeah, so the first thing I was wondering about this is, in terms of the predictions, what are the dominant sources of uncertainty? Like when you do this marginalization over the kind of, like galaxy halo connection parameters for both the satellites and the host, is it the uncertainty in like the host halo properties that drives the overall uncertainty, or is it in the faint end galaxy halo connection?
Yeah, so I'll start by saying that most of my knowledge for this is fairly tied to these lower mass systems. So I don't know if this remains the case for like Milky Way mass systems. I showed some plots, but I haven't looked into them in as much detail. At these lower host masses, the host parameters are actually fairly impactful, because there can be a fairly large scatter in both the stellar mass halo mass relation, which then propagates to basically your estimate of what the halo mass is of the host. And that halo mass of the host is what basically gives you the normalization of this. And so I actually think they're possibly of comparable effect. It's only when you go to much fainter things that I think the galaxy halo connection is more significant. But kind of in the regime where we operate, kind of the beginning of the ultra faint regime, I think they're actually of comparable effect.
Yeah, that makes sense. I mean, that's similar to what we're seeing in doing the modeling for Saga, because we really just have the luminosities of the centrals. That's not a very tight handle on the halo mass. The other thing I was wondering about this is, in terms of like the subhalo population predictions, how is disruption of subhalos accounted for due to the galaxy, the central galaxy?
Yeah, so that's an assumption that I breezed over. I don't know if it's correct in detail, but a lot of people get away with assuming that the stellar mass of the satellite is tied mostly to its peak historical halo mass or similar quantity, your Vmax or whatever else you want, right? And so we don't actually include any explicit tidal stripping parameters. Part of this is because at these faint luminosities, my intuition is that I mean, it changes depending on what you think the density profile is. If you think it's chord, then it's a much different position. But there's so much dark matter compared to the stellar mass, and the stellar mass is fairly centrally concentrated, so that you have to strip a ton of the dark matter before you start stripping out the stars, right? And the other thing is, we initially thought that because these things were LMC mass hosts, that we could, quote unquote, safely neglect tidal stripping. It's actually interesting. In MADCASH, we found a tidally disrupting, like, -13 dwarf around an LMC mass thing, which turned out to be pretty interesting. And I did a little bit of modeling for that, but not a ton. So yeah, basically we neglect it entirely. And at least at these small statistical samples, I don't know how much of a difference it would make, but I think it would be interesting to try to include something, especially as you get to larger statistical sizes where it would make more of a difference.
Yeah, that makes sense. I guess the question of like how much of a difference it makes is tied to the previous question about how large the dominant, other sources of uncertainties are. I guess in the fire simulations, they've looked a little bit into satellite disruption around LMC centrals, and it's definitely weaker than in the Milky Way regime, where it's like a 50% effect around the LMCs. It looks more like maybe a 30%, 20% reduction of the amplitude of the subhalo mass function. So it's probably not the limiting, like, theoretical systematic.
Yeah, I don't think it is, but I also don't feel great ignoring it entirely. So hopefully we can like reach a middle ground there eventually.
So I had one question I wanted to ask. So, and apologies if I missed this, but do you assume that there is a scatter-free relation between subhalo peak mass and galaxy absolute magnitude?
No, not at all. So
Okay.
actually one of the core components is including the scatter, because one of the components is formulating the probability of a halo mass given a stellar mass, which you have to do through Bayes' theorem, because the scatter around the stellar mass halo mass relation gives you like the probability of a stellar mass given a halo mass. And so one of the primary components is that inversion through Bayes' theorem. So no, we absolutely include scatter on that. And then I alluded to it a couple times, but we're actually not going directly from halo mass to luminosity. We're going halo mass to stellar mass, and then we're using the color distribution to get the stellar mass to light ratios, which then convert the stellar mass into the luminosity. So there are a couple extra steps there.
Got it. Okay, so that's good. And then, so kind of following up on that, is you change the particle nature of dark matter. So in some of the models you were showing that use like warm dark matter, are you concerned that at the low masses you then need to change the relation between the subhalo mass and galaxy mass?
In general, absolutely. It would be nice. It would be nice for this to be the part where the inference might be able to come in, because observationally, the types of stellar mass halo mass relations that I'm using, if you're optimistic, they might be robust to the like very, very bright end of classical dwarfs. If you're like quite optimistic, but basically they aren't constrained at the masses that we're interested in. And so one of the things I thought was interesting about Ethan's work is that that's he's doing inference on that galaxy halo connection directly. The reason we didn't do it here is just because the sample is so limited that I don't think it would be meaningful. But in general, I think you would have to.
Yeah, great, thank you.
Mhm.
Any other questions for Chris?
If we have extra time, I do actually have more slides I'd like to show. I just wasn't sure how many questions we were going to get.
Yeah, we still have like, yeah, a good 6-7 minutes. So if you have a couple of things you want to show, go for it.
Great, I'm glad. So another survey that I worked on and continue to work on is MADCASH. This is very similar in objective to LBT-SONG. So we're looking at, again, LMC mass hosts, but it's very different in terms of the data. So these come from HyperSuPrimeCam on the Subaru 8-meter. And the advantage is that it's a much wider field viewer. So if I remember correctly, the field of view is like 1.5 degrees on a side. So it's much bigger. And then we actually have between 4 and 7 pointings per galaxy and calibrated to try and map the entire virial volume. And so this field of view correction that I did, hopefully we won't have to do that for MADCASH. And we're, again, reaching similar depths. So I think fiducially MADCASH reaches like 26.5 magnitude, where LBT-SONG, depending on the band, is like 27 to 27.5. But MADCASH has better seeing. So there's some trade-off in terms of depth, which just has to do with overall exposure. But the seeing is better, so you have less blending problems. And so one of the interesting test cases that we had in MADCASH is that, as I mentioned before, we discovered tidal tails of this like magnitude -13 dwarf around this LMC mass thing, which was quite interesting also because it's at quite a large projected radius. I think in projection like over 100 kiloparsecs away. And so I did a fairly basic analysis for this because it wasn't it was mainly an observational paper with a little bit of interpretation. But what I did was I drew similar systems from, I think at the time, I think this was Illustris TNG 100. And basically I did some mock observing of these systems. And at left, I don't know why this is the plot that I made, but this is the radial velocity versus this is the proper 3D radius in simulation space. But then I impose a tidal disruption criterion. So this is based on some work that like Jorge Penarrubia and Frank Vandenbosch have been doing. But basically I'm saying that the present day halo mass has to be less than 10% of the infall mass. And this is motivated by the fact that in order to strip the stellar component, you have to eat away most of the dark matter halo first. And so this panel is mostly just to compare the number of systems. I think only 10% of the DDO44 analogs in these systems showed such a degree of tidal disruption, and only 3 of them have proper 3D radii that are larger than the observed projected radius. And so I don't remember if I did the proper like orbital analysis to see what the apicenters of all these things were, but it seems relatively rare to have a dwarf like this stripped this heavily at this large of a projected radius. And so we did a couple calculations to basically say that this is likely to be a highly eccentric, somewhat recent orbit, because all of these things are like relatively old orbits and that have experienced decay due to dynamical friction over time. But this seems to be a somewhat rare system with a high orbital eccentricity. Some, I think, slightly more interesting work has to do with two of the dwarfs that were discovered in MADCASH. So this one here is MADCASH 1. This is a luminosity -8 dwarf. This is the HSC image, and then this is the HST image, and you can see the difference in the CMDs there. And there's also MADCASH 2, which is slightly brighter at -9. MADCASH 2 is fairly interesting because the CMD shows a population of both asymptotic giant branch and blue loop stars. And you can see in the positional diagram that there's a good portion of them that are centrally concentrated in the dwarf, which means that these are likely to be real member stars. When we look at the CMD, we can attempt to use some modeling techniques. I did this based largely on Andrew Dolphin's older work and some of Dan Weiss's, but we can model the CMD using basically a linear combination of isochrone models. And so if you look at the purely ancient model, this is just like a 12 gigayear population with metallicity -2, I think. You can see that it doesn't agree super well with the color magnitude diagram of MADCASH 2. There's this relatively large population of very faint things. And there's also these blue loop and kind of asymptotic giant branch stars. Restricting ourselves to a relatively coarse grid in terms of what stellar populations we consider, we find that at minimum, we require 2 additional stellar components to model this: an intermediate age population, which is between 1.1 and 1.5 gigayears old, and and the intermediate is about 10% of the overall stellar mass, and the young population is about 1% of the stellar mass, and it's 400 megayears old. So this by itself maybe isn't super interesting, but MADCASH 2 is completely undetected in H1 with a limit of 5 times 10 to the 4 in H1 mass. So that corresponds to a stellar mass to H1 mass ratio that is, I think it's 3 or greater. So it's quite H1 deficient compared to the field. And so how do we explain this? It looks like I don't actually have time to go into the rest of the slides, but like I said, I do some work on environmental quenching as well. And if you're interested, we can potentially schedule a follow-up call with people who want to talk about that. And yeah, thank you so much for having me.
Great, thank you, Chris. Yeah, I think we're basically out of time. It was really good to see that additional work. Yeah, so thank you again for a very nice talk. Thanks everyone else for joining us.